So the example we're doing is number 4. We've got a vehicle with a mass of 1,250 kilograms. It's got a combined stiffness of 50 kilonewtons per metre, so it's 50 times 10 to the 3 newtons per metre. And the stiffness, the damping, is given by loss angle. So I'll just write delta is 20 degrees. We'll talk about that in a minute. It says it's driven over a road in which the vibrational input can be characterised approximately by a constant spectral level of 0.001 g squared per hertz. So our input spectral density, okay, so if I write S input, is 0.001, this is in fact in terms of F because it's in hertz, g squared per hertz. So there's our input. And like I said, it's in terms of frequency, not frequency in hertz, not frequency in radians per second. And the question is, find the root mean square vibrational acceleration level of the car. Now, with this sort of problem, you can consider it to be a base excitation type problem. And so that we can model it as the mass of the car, okay, M, connected to a spring and a damper, and then connected to a base. Now the base is essentially the road, and that road is moving up and down. Okay, so we've got a base excitation down there, where this is, I call this X subscript B, so the excitation of the base, or motion of the base, and I call this X, which is the motion of the car. Here we've got the spring constant K, damping constant C. And what I'm going to do is I'm going to work out, first of all, what my C value is going to be. Now we know, back on the equation sheet, you'll know that the loss angle, or zeta in fact, is 1/2 tangent of the loss angle. That's on your equation sheet. When you're given something with a loss angle, you know it's got damping, and that's the equation that will give you an approximate value of zeta. Now we know zeta is C divided by 2 root mk. So you can see we've got an equation here that we can rearrange for C. So that means that C is going to be root mk times by tangent of delta. So we can work out C. We'll come back to that in a minute. So what we need to do is we need to get the equation of motion for this system. So it's quite clear if we take the motion of x, mx double dot, Newton's second law is all the forces that are being attached to it. So we've got a minus c times by x dot minus xb, okay, minus k x minus xb. Now we've got the minus and that, so we've got the minus in there because it's the relative displacement and the relative velocity between those two things that will act on the damping and the spring. Okay?
Ben,
Yes?
just a question, sorry, what did we say S was, the loss angle?
Delta that's delta.
Oh yeah.
Delta is what's known as a loss angle, and you can relate the loss angle to C by this equation here. Okay? And we'll work that out in a minute. So this is, from taking the free body diagram of this mass up here, we can work out the motion of x. So mx double dot, okay, is minus c x dot minus xb dot. So you have to take the relative velocity between the two. Okay, and then you've also got the spring stiffness, which is k times by the relative displacement between the two. So there's your equation of motion. We rearrange it to put everything on one side. Mx double dot plus cx plus cx dot plus kx is going to be equal to cxb dot plus kxb. There's our equation of motion. So all the x's are on one side and all the xb's on the other side. Xb is my input and x is my output. Okay, so I can work out the frequency response function. And so if I rearrange this, if I make the substitution that x is big X e j omega t, and xb is big XB e j omega t. Make the substitution, I end up with an equation that looks like minus m omega squared plus j c omega plus k times by big X equals j c omega plus k times by big XB. Now here I've got the input and output in terms of displacement, so I can therefore say h omega. So we've got the output divided by the input. That's right, yeah, xb. So I've got j c omega plus k divided by minus m omega squared plus j c omega plus k. That's my complex frequency response function. Now this is in terms of displacement, but like I said, if you know displacement, you can work out velocity and acceleration. And it just so happens that if we took the acceleration, okay, you get the same thing. So this equals x double dot divided by xb double dot. And that's important because what we're trying to work out is the RMS of the acceleration, not the displacement. So there's our h omega. We then move on, so that's obviously the first thing that we need to know. We then move on to the equation where we know that s of x double dot, our output is going to be h omega modulus squared times by s xb double dot. Okay, there's the first important equation. And we know that the expected value of x squared is going to be the integral of s x double dot d omega. And that's between minus infinity and infinity. And s we know is a function of omega. And so we know that this is the integral of minus omega, from minus infinity to infinity of s x b double dot times by h omega squared. Now we know that this value, the power spectral density of the input, is a constant. It's given up here. And so this is going to be some constant, s omega. That's a double-sided integral. We'll write it like this. Times by the integral from minus infinity to infinity of h omega, the jc omega plus k, divided by minus m omega squared plus jc omega plus k. So we now need to work out what both of these things are. Okay, so let's take a look at this bit first. Well, we've got, this is going to be s of f divided by 4 pi. So we have a 0.001 divided by 4 pi g squared per hertz. Sorry, that's g squared per radians per second. Okay? Because we had SF up the top, as given in the question, up here, is 0.001 g squared per hertz. But then to get it into terms of omega, you must divide that by 4 pi. Okay? And that's the relationship that we saw in the notes. Okay? Between SF and S omega. you have to, SF is 4 pi times by S omega, so obviously you can divide SF by 4 pi and you get your term in terms of radians per second. So that's the first bit. This second bit here, the integral from minus infinity to positive infinity of jc omega plus k divided by minus m omega squared plus jc omega plus k squared. Well, this is where we use our solution to that integral, okay? And we know the solution to this bit. We've got pi, and then we have the equation that we have on the formula sheet, which I'll just access briefly. B naught squared divided by A naught, all multiplied by A2, plus B1 squared divided by A1, A2. Now in this equation we can see that B naught is K, B1 is C, A naught, what have we got? A naught is K, A1 is C, and A2 is M. Okay, so if you look at this, the equation, which is, like I said, on the equation sheet or on the bottom of page 167, you can see that you can match up the solution with the terms in this function. Okay, and by matching those up, you can therefore work out the solution. So that's going to be pi. We've got b naught squared, so that's k squared, divided by a naught, which is k, multiplied by a2, so that's m, plus b1 squared, so that's c squared, divided by a1, a2, so that's c times by m. So we've got a solution to this bit, which is here, and we've got a solution to this bit, which is there. So since we know what this is, and we know what this is, we can multiply them together to get EX squared, EX double dot squared. So I'll do it on this page. E times by pi. This k squared divided by k is obviously k, multiplied by m, plus c squared divided by cm. The pi's cancel. Now, before we can do this, we need to work out what k, m and c are. K and m we've been given. C we said, so as an aside, I'll just draw a dotted line. C we said up here was root mk times by tangent of delta. So that's root m, which is 1250, k, which was 50 times 10 to the 3, times by tangent of 20 degrees. And if you do the sums, this comes out to be 2.877 times 10 to the 3 Newton seconds per metre. So there's our value for C. So we can now plug the values in. We've got E x double dot squared is 0.001 divided by 4 times by 50 times 10 to the 3, 1250, so that's km, plus 2.877 times 10 to the 3 squared divided by 2.877 times 10 to the 3, 1250. That's just a matter of plugging in the values that we had for M, K, and C. So that comes out to be 0.0049 g squared per radians per second. And obviously x RMS is the square root of the x squared. So the answer, XRMS, is 0.07 G. So I'll just run through this question again. So we'll start at the top. So we've got a car, it's got a mass of 1250, the stiffness is 50 kilonewtons per metre, and it's got a certain amount of damping, which we can work out because we've been given the loss angle. Okay? The input power spectral density is a constant value of 0.001 g squared per hertz. Okay, that's in terms of frequency in hertz. Okay, and this sort of problem could be considered as what's known as base excitation. So the first step is to work out h omega based upon our model. We take Newton's second law of the mass that's of interest. So the sum of all the forces is mass times acceleration. And so mx double dot equals all the forces that are acting upon it, which is the damping force and the spring force. And you go through the process and you end up with h omega, which is output divided by input. So you end up with jc omega plus k over minus m omega squared plus jc omega plus k. Now, although this is in displacements, the same relationship could be said about acceleration. So you can just say x double dot over xb double dot gives us the same thing. Now, from the theory, we know that the power spectral density of the output is the power spectral density of the input multiplied by this h omega with the modulus squared term. Okay? And we also know that the integral of the power spectral density of the output gives us our mean square term. Okay, so the integral of this bit, which is over here, will also give us our mean square term. Now, I'm rewriting this down here. We know that this term up from the top is a constant, so we can take that out of the integral because that's not going to change. S omega. And then we've got the integral here, minus infinity to plus infinity of our h omega term, modulus squared. Now the thing is, well, we can work out what this is. We know that that's a constant, okay, and the constant term was 0.001 upon, g squared per hertz. To get it in terms of omega, we must divide by 4 pi, which is where this 4 pi's come from. And so that's now g squared per radians per second. Okay, so that's the first bit. The second bit, we use our relationship, the integral relationship that we had, which the solution to which looks like this, when these terms have been defined. Okay, so like I said, that's on page 167 of your notes, and it's also on the formula sheet. Here's the formula sheet, and you can see the top equation is that relationship. So if you know the form of this equation, you can work out what the answer is. And here's as an example, okay, and it gives you the solution. So that's on the formula sheet, and so there's your answer. And so now we have the solution to this bit, and we have the solution to this bit. Okay, so we can solve that equation to find out what E x double dot squared is. And so you go through the motions there. So there we go. So I've combined them together. There's my 0.001 divided by 4 pi, which is my spectral density, times by pi times by the solution I had up here. That's this bit down here. That's in there. And then this process is just a matter of, well, we need to work out what C is. We worked out the equation for C up the top. This is plugging in the numbers to get a value for C. And then this is just a matter of plugging the things into the equation. The pi's cancel up here. Okay, you plug in the numbers into the equation, you get a value for the mean square. You take the square root of the mean square, you get your RMS. And the RMS comes out to be 0.07 g.